The area of work that I'm working on is called Garside Theory, and the subtitle for that would be Algebra, Combinatorics, and Computing on a Date. Right. I'm aiming to give you in the next 10 minutes a rough idea of what I'm working on, why I'm doing this, and I mentioned some collaborators, recent papers, and recent grants. So let's first go to the what. I was asked to give a TED-style talk, so please I'm apologizing in advance if this is too basic, but just in case you've got non-mathematicians here, I would describe myself as an algebraist. And if you had to explain what algebra is to somebody who doesn't know any mathematics, the first thing that you'd say is that it's an area of pure mathematics. And the second thing that you should probably say is that algebraists don't work with decimal numbers. But instead what they're doing, they work with more abstract discrete objects. So another way, a bit tongue-in-cheek, to put this is to say that algebra is about structures, maps, and everything. So if you look at an algebraic proof from the book, one of the really great proofs, half the time they would, more than half the time I guess, they would involve defining some kind of structure and a few maps preserving this structure, and then put the law to good use and eventually prove the theorem. So, in other words, algebra is about abstracting. If you check a definition, a dictionary for a definition of abstraction, it tells you that abstraction tries to achieve a deeper understanding by formulating generalized ideas or concepts through extracting common qualities from specific examples. Now, these days, unfortunately, the label abstract is by some people used in a negative sense, also almost as the opposite of relevant or useful. And unfortunately, you don't hear this only from students. So, when preparing this talk, I came across a quote that I thought I'd put in. It says, "The research worker in his efforts to express the laws of nature in mathematical form should strive mainly for mathematical beauty. He should take simplicity into consideration in a subordinate way to beauty. It often happens that these requirements are the same, the requirements of simplicity and beauty are the same, but when they clash, the latter must take precedence." Now, it would be very surprising or remark-worthy if it came from a mathematician, but it doesn't. It comes from Paul Dirac, one of the founders of quantum mechanics. Now, Dirac was definitely somebody who wanted to use mathematics, not do it for its own sake. He saw mathematical beauty, the structure, the abstract structure of a consistent mathematical theory, as one of the main indicators of that theory being true and thus ultimately useful for him. Now, I can imagine people questioning whether this is still relevant in our context now. What they might say is firstly that, well, Dirac's definition probably didn't involve student surveys or KPIs, and that would probably be right. And secondly, they'd point out that these days we've got quantitative measures on how to measure the usefulness of research, and actually we can call it impact. So, if you were in a conversation with somebody, what could you say? Well, you could answer with another quote, like this one. "The theory of numbers has always been regarded as one of the most obviously useless branches of pure mathematics." Now, this gem is from Hardy. And if you haven't seen the quote before, you could think that it's a scathing damnation, if not of pure mathematics, then at the very least of the theory of numbers. But you'd be wrong. Hardy actually stated this as a virtue of number theory. And to make sense of this, you need to point out two things. Firstly, the year in which it was said, and secondly, that Hardy was a radical pacifist. So what he meant was that number theory is a beautiful theory, an abstract theory, and obviously useless in the sense it doesn't have any obvious uses, or these days we might say impact zero, and hence in particular you can't abuse it by applying it for militaristic purposes. So, looking at this from today, you would feel obliged to point out that in 1977 the RSA algorithm was published. It might have been discovered earlier, but it was published in 1977. And today, number theory and its extensions, algebraic geometry and so on, form the basis of virtually every established coding scheme and cryptographic scheme that exists. So chances are you've used it today, if you've checked your UWS email, or if you've done internet banking, you've used something based on number theory. As far as the militaristic purposes are concerned, suffice it to point out that the American National Security Agency these days is if not the major funding source for research in this area of pure mathematics. So if you wanted to compare the obvious impact measures of research to Dirac's feeling or Dirac's indicator of research, that will clearly be 1-0 for Dirac. So after that small commercial break, what's the mathematics that I actually do? Andrew's already mentioned this very briefly. The objects that I'm really working on are called Garside groups, and I can't tell you in 10 minutes what they are, but they are generalizations of something that you do know, namely of so-called braid groups. Now, if the group bit scares you, you certainly know what braids are. Just think of braiding long hair. If you want to do this a little bit more formally, imagine n strands running from the left to the right. Here they are. Then you can braid them by intertwining repeatedly pairs of adjacent strings. Might look like this then. Now note that these are not just crossings. The over and under is important. You can't just draw solid lines here.